Hey everybody. So we've covered some identities so far. You have an identity book. That's all great. Let's do a little exploration here. How can we use what we've learned to find the trig ratio of double an angle? So let's look at sine, for example. What if I wanted to find the sine of double an angle? So the sine of 2 times some angle, which we're going to call x. Well, how can we use what we already know to help us figure this out? Well, the sine of 2x, of course, is the sine of x plus x. Okay. Now, why would I write it that way? Well, because now I have this as a sum, and we have some identities, S-U-M identities, S-O-M-E identities, some identities dealing with sums that we could possibly use here. So how do we find the sine of the sum of two angles? Hey, I'm going to be taking a look here, make sure I get this right. So this, of course, would be sine of x cosine of x plus cosine of this second angle times the sine of the first angle, and we have that. Now, notice that this is a product, so the order that we write that doesn't matter, it's commutative, right? So we have the sine of x cosine of x plus the sine of x cosine of x, which would be 2 sine of x cosine of x. So the sine of 2x is equal to 2 sine of x cosine of x. Okay, and that's our first, what we call double angle identity. We can take the sine of double an angle by taking 2 times the sine of the original angle times the cosine of the original angle. We don't have the double angles in there anymore. We have the original angle. So that's the first of our double angle identities. Okay. So I have that one written right here. Now, I would be super proud of you guys if you pause the video and put some effort into determining the cosine of 2x and the tangent of 2x. I think you guys can do this. Now, I know I have 3 equal signs for cosine, but see if you can come up with at least one of them. Okay, maybe not all 3. Just come up with one double angle identity for cosine and the double angle identity for tangent. All right, okay. Let's take a look at the cosine of 2x together. Whoops, wrong button. So the cosine of 2x would be the cosine of x plus x, which is, following my cosine sum identity, that would be the cosine of x cosine of x plus, nope, we gotta switch our sign, don't we? Minus sine of x, sine of x. Well, what's cosine of x times cosine of x? Well, that's cosine times cosine, which is cosine squared of x. And this would be sine squared of x. So I hope that's the one that you're able to come up with. That's our first double angle identity for cosine. Now, what about these two other equal signs? There are some other options, some things that we could do with that. I'm actually going to split this into 2 different pieces. And what I'm going to do here with this one is I'm going to replace the cosine squared using the Pythagorean identity that cosine squared plus sine squared equals 1. So cosine squared equals 1 minus sine squared. I'm going to use this alternate Pythagorean identity and replace that with a 1 minus sine squared. Now, why would I do that? Well, because now we have 1 minus sine squared, and we still have a minus sine squared. So this is 1 minus 2 sine squareds. Okay, so I have a double angle identity for cosine that only involves the sine function. Okay, so that's our second one. 1 minus 2 sine squared. Our third, okay, is let's use an alternate Pythagorean identity for this one and write this as cosine squared of x, so that's this first one, minus, what's the alternative for this? 1 minus cosine squared. Now notice I'm being careful here. I'm subtracting. I put all this in parentheses so I make sure I distribute my negative. Now I combine my like terms. I have 2 cosine squared of x minus 1. So here I replace sine squared of x with 1 minus cosine squared, and we get our third Pythagorean identity. 2 cosine squared of x minus 1. Look, notice these look pretty similar. It's kind of neat. Lastly, tangent. This one's a little bit simpler. The tangent of 2x is the tangent of x plus x. And if we follow our sum identity for tangent, this is the tangent of x plus the tangent of x over 1. Now on this one, the sign switches. It was a sum, it becomes a minus. Tangent of x, tangent of x. In the numerator, I have 2 tangents of x. In the denominator, I have 1 minus. This would be a tangent squared. So that is our tangent double angle identity. And I hope that was one you were able to come up with as well. Okay. You know, I just had a thought. I'm going to pause my video, double check one of my examples here. Yeah, I decided to add another example in here real quick. Sine of pi over 3. Let's see how we can use our double angle identity to check that this really is what it is. Now I know we can look at our unit circle to determine the sine of pi over 3. Hopefully we don't even have to look at it, we just know it. But I want to just use this to show that our double angle identity really works. So notice that we're taking the sine of pi over 3, and pi over 3 is what? 60 degrees, right? So 60 degrees is actually double 30 degrees. And 30 degrees is pi over 6. So would you agree that pi over 3 is double pi over 6? So this allows us to use our double angle identity now for sine. And sine, double angle identity, is 2 sine of x cosine of x. So I'm going to put a 2 here, and I'm going to take the sine of our angle, pi over 6, not the original, okay, not the original here, pi over 3, but the angle that is double of, which is pi over 6. So I take sine of pi over 6 times, continuing on with my identity here, times the cosine of pi over 6. Now, what is the sine of pi over 6? The sine of pi over 6 is 1/2. What's the cosine of pi over 6? Root 3 over 2. And what happens? The 2 times 1/2 cancel, and we have root 3 over 2. Isn't the sine of pi over 3 root 3 over 2? Yes, it is. It worked. All right, continuing on. Let's simplify 4 times the sine of 5 theta cosine of 5 theta. Okay. Now, here's what I notice here. I have a sine times a cosine. The angles in there are the same. It reminds me a lot of this side of the double angle sine identity. Okay. However, we don't have x's, we have 5 thetas. So here's what we're going to do. Okay. Let's just write down our double angle identity for sine. Okay. Now to help me think about this, because sometimes I struggle here when I switch my variables, we don't have x's in this problem, we have thetas. So let me rewrite it with thetas. All right, so here's what I want you to do. Compare this to this whole thing now? Well, instead of a 4, we have a 2. So I think that we could multiply each side of our equation by 2. That gives me 2 times the sine of 2 theta equals 4 sine theta cosine theta. Now, this is a little bit closer to that. What the issue is now is just our angles. We have thetas here, and we have 5 thetas there. Okay. So what we'll do here is we'll replace theta with 5 theta. And if we do it there, we do it there, and we do it there. This gives us 2 times the sine of, well, what's 2 times 5 theta? 10 theta equals 4 times the sine of 5 theta cosine of 5 theta, which is now exactly what this looks like. So we simplify this to be that. It's 2 times the sine of 10 theta. All right, carrying on. Okay. If the cosine of x equals negative 4/5 and it is in quadrant 3, that means is would be x is in quadrant 3. Find the exact value of the cosine of 2x. And now we have a couple options here. I hope I have enough time in this video for both. We want to find the cosine of 2x. Now remember that we have 3 options for our double angle formula for cosine. Now because we know what the cosine of x is, I'm going to choose this one that only has cosine in it. This has cosine and sine. This has sine. This has something that we already know. This is 2 cosine squared of x minus 1. Now, I'm going to remind you that the cosine squared really means this. Cosine of x squared. And do we know what the cosine of x is? Yes, we do. The cosine of x is negative 4/5. So we can substitute negative 4/5 in for the cosine of x, and now we can figure out what this is. When I square negative 4/5, I get 16/25. When I multiply that by 2, I get 32/25. And when I subtract 1, let's see if I have enough room. Yes, I do. I get, well, 32/25. 1 is 25/25, so this gives us 7/25. Pretty neat there. Now let's talk about an alternate option here. Okay. Let's say I wanted to use the first identity that we came up with for our double angle, cosine squared minus sine squared. This requires me to know what the sine of theta is in. And that's why this third quadrant comment is really important. Okay? If we are in the third quadrant, okay, we are down here. Okay? And we know that the cosine of that angle is equal to negative 4/5. So this is negative 4, that's 5. What is this? Well, this is a 3, 4, 5 triangle, isn't it? But we're in the third quadrant, so that has to be a negative. And because we're in the third quadrant, the sine of x is a negative 3/5. And if I didn't tell you we were in the third quadrant, we could have been up here and the sine could have been a positive 3/5. So that's why that would be important. So now let's substitute in the cosine squared. Well, cosine is negative 4/5 squared. The sine is negative 3/5. We square that. I'm racing the clock here. This is 16/25 minus 9/25, which is 7/25 again. Very good. All right, so that's what I wanted to show you with the double angles. We've added a bunch of double angle formulas. Make sure that you put that in your identity book. Put this into practice. Thanks for watching. See you later.